you have a filter and you have a matrix or an image which on which you convolve this filter, which is of a smaller size than the original image. And we saw the concepts of padding, strided convolution, convolution over volumes, and we saw different examples of the convolution neural networks. We talked about pooling layers, so you can have max pooling or average pooling, and we saw the examples of the convolution neural network, and then the different popular types of CNNs like LeNet, AlexNet, BGGNet. So then we discussed about the residual networks which have skip connections or are also known as the ResNets. And then we were here looking at the different architectures of these popular CNNs. Okay, so then I think we did not discuss about the Inception networks, right? Did we?
No, sir.
Can anybody confirm? Okay. So we did not discuss in this class, but if you guys remember in an earlier class, I had talked about Inception networks. So yeah, where were we? Okay, I think we have discussed the Inception network before. We have discussed it once, and what we basically have in Inception network is okay, fine. Is typically we have, so in a traditional CNN we have a kernel of the same size, but in Inception network, in a like within a layer, like between two layers, you can have different types of kernels. So you can have kernels of size 1 cross 1, 3 by 3, 5 cross 5, and you can also do max pooling. So you would do this typically, and you would then concatenate the output of all these kernels. One important thing to note here is that you would keep the padding as same, so that otherwise there will be a mismatch in the output uh, when you applied kernels of different sizes on the input data set.
Sir,
Yeah.
I'm not sure, but your screen is not visible for me. I don't know about others.
Okay. Is it visible for others?
Yes, the screen is visible to me actually.
Okay.
Okay,
Okay.
okay.
Maybe. Okay. So in Inception network, you have all the different types of kernels within two layers. And in this one, we can see that we have an input to the Inception module, which is 28 cross 28 cross 192, and the output is 28 cross 28 cross 256. And we have done all the convolutions and poolings that we might want, and we will let the neural network learn and decide which one it wants to use. So there is a problem of computational cost in the Inception network. So if we are focused on just 5 by 5 convolution. So there are 32 filters, and the output is 28 cross 28 cross 192. So in this one, so in this one we can see the output is 28 cross 28 cross 192, but it should be typically like, if you have 32 filters, then it should be 28 cross 28 cross 32. And so you will end up in like uh, you will you will face a big problem of computational cost if you are using this kind of inception network. But it is beneficial to use such a model which gives a kind of flexibility to your data to basically choose what it wants, like which kind of kernel it would prefer. So yeah, one by one convolution, they're calling it as the bottleneck BN. And so this is another schematic diagram of the convolution of the inception network. And to make an inception network in TensorFlow Keras, so Keras was independent before it came under the umbrella of TensorFlow. And so you will what you will basically do is you will apply con 1 cross 1, con 5 cross 5, 3 cross 3. I mean, you can choose what kind of filter you want, and then you have these layers, and then you will concatenate all of them. So this is like the inception module of your inception network. And the inception network consists of concatenated blocks of inception module, and the name Inception was taken from a meme image from the Inception movie. And this model, this big model that you can see, this is known as GoogleNet. So GoogleNet was also, I think, a model which competed for the ImageNet challenge. And sometimes max pool block is used before inception module to reduce the dimension of the inputs. And you can see that there are 3 softmax branches at different positions to push the network towards its goal. So let us see. Okay, yeah, so there is this one softmax, and then we have another softmax, and then you have another softmax. So they are saying that there are 3 such branches, and it helps to ensure that the intermediate features are good enough to learn, good enough to the network to learn. And it turns out that softmax 0 and softmax 1 gives the regularization effect. So you can check the values of softmax 0, softmax 1, and see whether you can ensure whether your model is learning. And since the development of Inception module, the authors and others have built other versions of this network, like Inception version 2, version 3, version 4. Also, there is a network that has used the Inception module and ResNets together. So we have seen the neural networks and ConNet architectures, and it turns out that these neural networks are difficult to replicate because there are some details that are not present in these papers. And other reasons, like there are concepts of learning rate decay, wherein you will decrease the learning rate with the increasing number of epochs, and parameter tuning. So we don't, like, the papers generally don't provide in detail information of how they did the parameter tuning. And a lot of deep learning researchers are now open sourcing their data sets on their codes on GitHub. And if you see a research paper, want to build over it, first thing you should see is the open source implementation of that paper. So some advantage of doing that is that you might download the network implementation along with its parameters or weights, and authors might have used multiple GPUs, spent some weeks to reach the result, and it's right in front of you after you download it. So then now we'll see the concept of transfer learning. So we have discussed transfer learning, wherein we basically train a model for a particular task A, and for a similar task B, we can reuse the model which was trained on the task A. So if you are using a specific neural network architecture that has been trained before, you can use the pre-trained parameters or weights instead of random initialization to solve your problem, and it can help you boost the performance of the neural network. So the pre-trained models might have been trained on large data set like ImageNet, or there is another data set known as Microsoft Coco. So this is basically for object detection problems, and it's not just classification, like you have to tell in the image where exactly is the object. So our Pascal and took a lot of time to train those parameters or weights with optimized hyperparameters. So this can save you a lot of time. For example, if you have a classification problem which contains 3 classes, uh, Tigger, Misty, and Neither, you don't have much data to train, a lot of data to train a neural network on these images. So Andrew recommends to go online, download a good neural network with its weights, and remove the softmax activation layer at the end of the neural network, and put your own layer at the end, and make the network learn only the new layer while the other layers weights are fixed. So that is if you are having less data set, so you can use this strategy. And the frameworks, so the TensorFlow, PyTorch, or Keras, so they have options to make parameters frozen in some layers using trainable equal to 0 or freeze equal to 0. And one of the tricks that can speed your training is to run pre-trained neural network without final softmax layer, and get an intermediate representation of your images, save them to disk, and then use this representation to a shallower neural network, which can save a lot of time. It's like converting your images into vectors or some kind of embedding. And another example is if you have a lot of pictures of cats. So one thing you can do is to freeze few layers from the beginning of the pre-trained network and then learn the other weights in the network. So some other idea is to throw away the layers that aren't frozen and put your own layers. And then he talks about another example wherein if you have enough data set, you can fine tune all the layers in your pre-trained network, but don't random initialize the parameters. So don't do random initialization, leave the learned parameters as it is and learn from there. So that can be another strategy to do efficient training. Now comes the so this was about transfer learning, wherein you basically reuse a model which has been trained on a similar task before for various reasons, for doing a training faster, or if you have limited access to computational resources, or you have less data, or like, yeah, as we discussed, if you want faster training. So then we have the concept of data augmentation, and you can, so the idea is, the hypothesis is, if you have more data, your neural network will perform better. And data augmentation is one of the techniques that deep learning uses to increase the performance of deep neural network. And a lot of computer vision applications need more data. So some of the data augmentation techniques which are typically used in computer vision, you can also try to use it in our field. They are mirroring. So you just mirror, so what it will do is create an effect that the left will become right, right will become left. The random cropping, rotation, shearing, you introduce shear in the image, so you introduce warping in the data, and you can also shift the colors. So for example, we add to red RGB some distortions that will make the image identified as the same for the human, but it is different for the computer. So, and so in practice, the added values are pulled from some probability distributions, and these shifts are very small. Makes your algorithm more robust in changing colors in images. And there is an algorithm known as Pca Color Augmentation that decides the shifts needed automatically. So data augmentation also has some parameters, hyperparameters. A good place to start is to find an open source data augmentation implementation, and then use it for fine tuning the hyperparameters. Now, so we have seen all the building blocks of convolution neural network, a lot of the concepts. So we'll talk about the state of the computer vision field, and each for each specific problem, he says that we may have a little data or lots of data. For our case, we have lots of data, but we are limited by a lot of places where we need good quality satellite data sets. That is something which is lacking. So then speech recognition problems, for example, has a big amount of data, while image recognition has medium amount of data, and object detection has a small amount of data nowadays. So object detection, as we discussed, you have to exactly in the image, you have to tell where exactly the is there a question? Excuse me, I think if somebody's mic is on, can you turn that off? Yeah, okay, thanks. So speech recognition problems, for example, has a big amount of data, while image recognition has medium. Yeah, so object detection, we were discussing that. So that is if you just search for object detection, that's like going a step forward in identifying whether this image has a dog or not. So rather than just classifying this image as 0, 1, or you exactly you have to get the bounding box where that particular object exists. So this is a dog, this is a bicycle, this is a car. So you have different state of the art algorithms, like one of them is known as YOLO, you look only once, and these are also embedded these days in your smartphone cameras. So you can see that this is online or live object detection, wherein the model has identified the different objects with high accuracy, similar to humans. So you have, so the data set, amount of data set in object detection is definitely less as compared to the image recognition problem. And if your problem has large amounts of data, so the researchers tend to use simpler algorithms and less of hand engineering. So you would, if you have a lots of large amount of data sets, so you would use big models, let the neural network do basic feature engineering. And if you don't have that much data, people tend to try more hand engineering for the problem. So like choosing a more complex neural network architecture, but we haven't got that much of data required in computer vision problems. So yeah, you can try hand engineering, and there are some tips for doing well on benchmarks or winning competitions. So train several networks independently and average their outputs, so merging down with some classifiers. After you decide the best architecture for your problem, initialize some of that randomly and train them independently. So you, after you have zeroed in on what architecture is the best, so you would basically you would initialize some of that randomly and train it independently. And doing these two things, it can give you a push in accuracy by around 2%. And but this will slow down the production of by the number of ensembles, also takes more memory as it saves all the models in the memory. And people use this in competitions, but few use this in real production. And so you can also do multi-crop at test time, so run classifiers on multiple versions of test data and average the results. So there is a technique called 10 crops that uses this. So this can give you a better result in production. And use open source. So use architecture of networks published in literature, use open source implementations is possible, and use pre-trained models and fine tune your dataset. So next we will talk about object. So if you guys have any questions, you can just jump in right away and let me know. We'll discuss that. So we were talking about object detection, and so object detection so we first talk about object localization. So object detection is one of the areas, and this is by the way from 2018. So related to 2018, he says that is doing great in deep learning in the past 2 years. And so first you have to do an image classification. So classify an image to specific class. The whole image represents one class. We don't want to know exactly where the object is. So usually one object is present. And classification with localization is basically you given an image, we want to learn the class of the image and where the class location. So we want to exactly know where in that image that object lies. So this is classification with localization. So we need to detect a class and also the rectangle of where the object is. So usually only one object is present. Now the third type of problem is object detection, and so you are given an image, and you want to detect all the objects in the image that belong to a specific class and given their location. So an image can contain more than one object with different classes. So for example, in this one, yeah, this is what we saw. Yeah, bicycle, dog, and car. Then there is another class of problem. So this is known as semantic segmentation. So for example, you can, if you see this is an image of an aircraft. So you want to classify each pixel of the image. Okay. So for example, this is sky, and you have building, then you have building, then you have an airplane, and then you have graphs. So you want to label each pixel in the image with a category label. And semantic segmentation, so it doesn't differentiate between instances, only cares about pixels. So it detects no objects, it just detects the pixel. So in the pixels, it would be classifying a pixel as 0, 1, 2, 3, or whatever the total number of classes are. And then you have like so if there are two objects of the same class intersected, which are intersecting, so we won't be able to separate them. And then you have the instance segmentation problem. So this is like a full problem. Rather than we want to predict the bounding box, we want to know which pixel label but also distinguish them. So you can see here we have a background and you have these instances. So these are three different types of objects in the image. So you basically have the first type of problem, which is image classification, then classification with localization, then you have object detection, then semantic segmentation, and then you have instance segmentation. So to make image classification, we use a convolution neural network with a softmax attached to the end of it. To make classification with localization, so if you have a single image and you want to tell the bounding box as well, we use a convolution neural network with a softmax attached to the end of it, and four numbers: bx, by, bh, and bw. So bx, by are some kind of coordinates x and y, and bh, bw correspond to the height and the width of the box to tell you where the location of the class in the image. So the dataset should contain these four numbers with the class also. So the first is the probability of an object, whether it is present or not. The second is bounding for the bounding. Second, third, fourth, and fifth are for the bounding box. And then the classes. So one hot encoded representation of the classes. Because see, first, this is also very important because the object might not be present at all in the image. So this kind of labeled data set you have to create. And then so the example, so as for example, you can have this label as 1, so the object is present. So 0, 0, so that is the those are the that is the center point, I think, of, or I think the leftmost corner. We'll have to confirm that. And then this is the height, this is the width, and these are the classes. So 0, 1, 0. So this belongs to the second class. And when the object is not present, so you give the so this probability class as 0, and then question mark means we don't care about other values. So the loss function for y that we have created is y1 hat minus y square plus y2 hat minus y square. So if y equal to 1, and y1 hat minus y square if y1 is 0. So, and in practice we use logistic regression for the probability class, and log likelihood for classes, and squared error for the bounding box. So you will basically, so this, if this is your y, and so if this is 1, so you will just take the y for the y predicted, and the y which is the ground truth, and then you will square it, and then you will basically calculate the sum of it. So that will be your loss. Okay, so yeah, and this one is plus dot dot dot, because this might also a single image might be outputting multiple y's, because one object might be belonging to a particular class, the other object might be belonging to another class. So in practice, so that is why you have this. And if your y1 is equal to 0, if there is no object, then you simply use y1 hat minus y1 whole square. And so for example, if you want to detect landmark, so landmarks which are present on the roads, and so in some of the computer vision problems you will need to output some points, and this is called landmark detection. So for example, if you are working in a face recognition problem, you might want some points on the face, like corners of the eyes, corners of the mouth, corners of the nose, and so on. And this can help in a lot of applications, like detecting the pose of the face. So why for this will be, so the first one will be there is a face, so whether the face exists or not. Then you have the x and the y location, the height and the width, and then you will have the class that this belongs to. So it has, you see, it has 64 different types of landmarks. So 64 classes. Another application is when you need to get the skeleton of a person using different landmarks or points in the person, which helps in some application. So yeah. Okay. So then you can do object detection. So we'll use convolution neural network to solve the object detection problem using a technique known as sliding windows detection algorithm. So for example, let's say we are working on the car object detection. Okay, the first thing we'll do is we'll train a convolution neural network on cropped car images and non-car images. So this is our training set. So this is our input image, and our label is 1. So this is a car. This is our input image. So label 1. This is a car. So the last two images, they don't have a car. So our label data set has y is 0. So our model that we are trying to build is that, okay, we are trying to input this car, and we have this connet model, and we are trying to output y. So that's something we are trying to train. And after we finish training of this connet, we will use we will then use the sliding windows technique. So in sliding windows algorithm, so you decide a rectangle size, split your image into rectangles of the size you picked. So each region should be covered. You can use some sprites, so common areas will be also encountered. Now for each rectangle, feed the image into the connet and decide whether it's a car or not. So then you pick larger or smaller rectangles and repeat the process from 1 to 2. You change the size of your rectangles, and then you just feed your rectangle into the convolution neural network and find out whether it's a car or not. and store the rectangles that contain the cars. And if two or more rectangles intersect, so choose the rectangle with the best accuracy. So we will see a so so two rectangles, when will they intersect? When they will contain the same object. So there is a metric known as intersection over union that is used to. So there is this metric known as intersection over union. So if you have yeah, so not this one. Okay, yeah, this one is fine. So if you have two rectangles so you have, if you remember, we said in the step number 5, store the rectangles that contain the cars. I mean the cars or some other object. So we have this rectangle which is the ground truth bounding box, which is the actual rectangle labeled by a human, and then this is the red rectangle which is the predicted bounding box. So now what you will do is you will so for example, if two such predicted bounding boxes have been saved, so you will calculate intersection over union. So intersection over union is you will calculate the common areas intersection between these two rectangles divided by the sum of these two rectangles, okay, or the entire total area of these two rectangles. And this number, intersection over union, so intersection over union is basically so area of overlap divided by area of union. For whatever rectangle that is higher, you will choose that for the as the predicted rectangle or the your predicted bounding box. So the problem with sliding window is the computation time. And in the era of machine learning, before deep learning, people used handcrafted linear classifiers that would classify the object and then use the sliding window technique. So the linear classifier makes the computation much cheaper, but in the deep learning era, that is so computationally expensive due to the complexity of the deep learning model. So to solve this problem, we can implement the sliding windows with a convolutional approach. And other areas too. So you can also compress your deep learning model. So convolution implementation of sliding window is as follows. So you turn your fully connected layer into a convolution layer. So predict image classes from 4 classes. So you have this image 14 cross 14 cross 3. So you have in all the channels RG and B. You apply a convolution. So you say 14 minus 5 plus 1 is 10. So you are not doing padding here. And then do a max pooling. So after doing max pooling, you have this as a fully connected layer, and then another fully connected layer, and then you have a softmax classifier. So what you can do is, so you see, so in the second part, what you see is you turn this fully connected layer into a conv layer. So you say this one is also 1 cross 1 cross 400 using a convolution with width and height of the filter, which is the same as the width and height of the input. And then so when you assume that this fully connected is also like a convolution layer, so the output is also a convolution layer. So then the convolution implementation then becomes something like this. So first, if you consider that the connet you trained is like something like this, wherein you have this image, you do the convolution, max pooling, the fully connected, but you assume that it's like a convolution. Now if we have a 16 by 16 by 3 image that we need to apply the sliding windows in. So this is your core algorithm which works on 14 by 14 by 3 images. So if now you have a 16 cross 16 cross 3 image and you're applying this sliding window algorithm to it, so you will see that first choose a 14 by 14 by 3. Okay, and so for 14 by 14 by 3, so this will be the output for, so you can see the blue ones as the outputs. So now if with the stride, I think the stride that they will use is 2. So then the output here becomes, no, stride is 1. So stride is 1 in the fully connected layer in this case. So then you have a 2 cross 2 as 2 cross 2 cross 4 as the output. So simply we have fed the image into the same coordinate that we trained, and the left cell of the result, the blue one, will represent the first sliding window of the normal operation. The other cells will represent the others. So it is more efficient because it now shares the computations of the 4 times needed. And another example can be that if you have a 28 cross 28 cross 3 image as an input, so then you will get something like a 8 cross 8 cross 4. So you can basically you can identify the object in at each pixel. So it has also got a depth. You can see what is the class, you can find out from here. So this example has a total of 16 sliding windows that share the computation together. And the weakness of the algorithm is that the position of the rectangle won't be so accurate. So this is the position of the rectangle, okay, that you will slide across the image, and it won't be that accurate, but maybe none of the rectangles is actually a fit on the object you want to recognize. So for example, you might want red, but what you might get is a this blue one. So you can see that for these are the bounding boxes, and these are then the classes. So you will find out the bounding box which has the highest intersection over union, and that is your bounding box of the image. So then another algorithm that became very popular is known as the YOLO algorithm. So this is the paper for YOLO algorithm. It stands for you look only once. And so in this one, you let's say if you have an image of size 100 cross 100. So this is an image of size 100 cross 100. These are the, I think the red ones are the actual ground truth labels of the bounding boxes. Now you place a 3 by 3 grid on the image. So you divide this into a 3 by 3 grid. So basically you have now so you have you have 9 images. So it says for smoother results you should use 19 cross 19 grid over a 100 cross 100 image. So but anyways, I mean we it's easier to see with an example of a 3 by 3 grid on this image. So now apply the classification and localization algorithm we discussed in the previous section to each section of the grid. So you apply a classification algorithm to each of these images, and then you see we discussed about the localization algorithm. So wherein we were we were trying to find out this was our uh, this was our output. So we know whether the object exists, what are the coordinates of the bounding box, height, width, and the classes. So this is our localization algorithm. So you basically apply classification first, and then you apply a localization to each section of the grid, and bx and by will now represent the center point of the object in each grid, and will be relative to the box. So the range, so bx and by, which is the center point of the object, which is what we were discussing, the x and the y, will now be relative to each of these grid boxes, and will be in the range 0 to 1, while bh and bw, so which is the height and the width, will represent the height and the width of the object, which can be greater than 1 but still a floating point value. So it will correspond to the actual height and width. and do everything at once with the convolution sliding window. If y shape is 1 by 8 as we discussed before, then the output of 100 cross 100 image should be 3 by 3 by 8. So for each grid box, so 3 by 3 is 9. So for each grid box, you will get 8 numbers. So first one will correspond to the probability of detection. Second one will be the bx, and the third one will be by. Then you will have the fourth one will be the height, fifth one will be the width, and then you will have the different classes. So we would consider 3 classes as we have seen in this example. So that's why 3 by 3 by 8, which corresponds to 9 cell results. And merging these results using predicted localization midpoint, so you will basically get the bounding box of the image. So we have a problem if we found more than one object in the, so that's about the YOLO algorithm. So you just in one go you have done the object detection. So you have identified the images in your large image of size 100 cross 100, but some problems still exist, like if you have more than one object. And one of the best advantages that makes this YOLO algorithm popular is that it has great speed and a convolution of implementation. So how is it different than other object detectors? So it uses a single CNN network for both classification and localization, localizing the object using bounding boxes. So in the next section we'll see some ideas which can make YOLO better. So one is, so we discussed this intersection over union, the function used to evaluate the object detection algorithms. It computes the size of intersection and divide it by union. So more generally, IOU, which is intersection over union, is a measure of overlap between the two bounding boxes. So for example, this purple bounding box and the red bounding box. So what is the kind of overlap between the two bounding boxes? So the intersection between the two divided by the union. And so finally, yeah, IOU is intersection by union. If IOU is greater than 0.5, then it is good. The best answer is 1. So best answer is when your two bounding, so the ground truth bounding box is exactly overlying the bounding box which is predicted by the model. Then another, so one thing that you can do is known as the non-max suppression. So one of the problems we have addressed in YOLO is that it can detect an object multiple times. So it can detect these blue boxes. So you can see that there are 2 cars in this image, whereas there are 5 bounding boxes. That has been identified by YOLO. So non-max suppression is a way to make sure YOLO detects objects just once. For example, each car has 2 or more detection with different probabilities, and this came from some of the grids that think that this is the center point of the object. So in the non-max suppression algorithm, you assume that you're targeting one class as an output class, and the shape of y should be the probability whether the object exists, bx, by, bh, bw. Now you can discard all the boxes with probability pc less than 0.6. So while there, so even after that, some of these boxes might remain. So yeah, for in this example, all of them will still exist. Now you pick the box with the largest PC output as a prediction. So for example, here 0.9. Discard any remaining box with IOU greater than 0.5 with that box output in the previous step. That is any box with a high overlap. So you discard any other remaining box which has got a higher overlap. And then if there are multiple classes or objects that you want to detect, you should run the non-max suppression C times once for every output class. So that will basically ensure that you're having one bounding box for one object. Now there is another concept of anchor boxes in YOLO algorithm. So I can see it's not only. So we will discuss anchor boxes and region proposals in the next class. I will quickly do at least one hands-on if I can in this session, because we have not been doing that. Okay. So now coming back to, so we have seen in we have seen the TensorFlow. So we were doing the TensorFlow tutorials. So we have done the TensorFlow quick start tutorial where we have seen the sequential class. So we took the MNIST dataset and then 28 by 28 images. We flatten them, build basically a deep neural network, very simple deep neural network which was showing good performance. And then we have seen TensorFlow for experts, wherein we have seen the gradient tape, and this is going more into the details of like performing the gradient descent algorithm. Now, after that, what we saw was we have seen this basic classification of fashion MNIST images. So we had this fashion MNIST dataset, and we built a model which, so for example, yeah, this is a shoe. So we built a model wherein we are again flattening and flattening the 2D images, and then we use the dense layers. We are not doing any convolution here. So then the next example that we have not considered yet in this case, or what we will do is we will do a convolution neural network example. So so this tutorial demonstrates a simple CNN to classify CFAR images. So CFAR is this data set. Okay, so you have the different classes: airplane, automobile, bird, cat, deer, dog, frog, horse, ship, truck, and then these are the images. So this tutorial uses Keras Sequential API. So as I told, there are two types of APIs that Keras has. With one is the sequential and another is the functional API. So you would first import datasets, layers, and models from TensorFlow.keras, and now this CFAR dataset, these days it's so this is also like a hello world type of dataset for CNN problems. So you would basically extract, so you would just get the train images, train labels, test images, test labels. So you would just download the CFAR dataset and then the train images, and then you would normalize them to the range 0 to 1. Now to verify, to basically have some kind of visual, do some basic visual inspection. So let's say we just plot some of these images and see what is there in the data. So the class names, we know what are the class names, or you can also do train labels. You can find out unique class names. So this is the total number of class names that we have, and so this is the, so then in our so train label, so this class name will correspond to, so for corresponding to each class name, the train labels is basically an index. So yeah, sorry, yeah, this class names is something we have seen from the data, and then we do a basic visual inspection. We plot these images, and then we just do print an X label with the class name. So you can see the label is printed at the bottom of the image. Now you would create a convolution neural network model. So there are these 6 lines of code which is creating the convolution neural network. So you would first create an object of the class sequential from, so this from model.sequential. So you can see this models is coming from TensorFlow.keras. So then you would do a model.add layers equal to layers.conv2d. So this conv2d will perform a convolution operation. It will take in as input, so it will the size of the filters or the number of filters is 32. The kernel size is 3 by 3. The activation that will be performed in addition to the linear combination with this convolution is ReLU. The input shape of the data is 32 by 32 by 3. So then you would do a max pooling 2D, and then you would do another convolution, another max pooling, and then you would add another convolution layer which has got 64 filters and a 3 by 3 convolution. So then you can do a model.summary, and with the model.summary you can see the layer name, the output shape, the parameters, the number of parameters in the or the weights in the that are in the layer, in that respective layer. So you can even add more layers on top of this this CNN. So you can say model.add layers.flatten. So you add a flatten layer. So that will basically flatten out the output of this layer. And then you have a dense layer with 64 neurons. And then another one is the final one is a dense layer with 10 neurons. So we have 10 classes as the output. So we use this dense layer with 10 neurons here. And the network summary shows now that 4,4,64 outputs were flattened into vectors of shape 1024. So 64 into 16, that I think, yeah. So this will be, they are saying it's flattened to 1024 before going through two dense layers. And then you compile the model. So in compilation you would provide the optimizer is Adam. So if you remember from the previous classes, Adam is a combination of RMS prop and momentum. So we also define the loss function. So loss is keras.loss, tf.keras.loss, sparse categorical cross entropy loss we are using this. So by using this loss, we can use the ground truth labels as the actual indices, whereas our predictions are one hot encoded predictions. So then another something that we also will check is the accuracy. So then you can say history equal to model.fit. So history will save all the information of the loss function. And then model.fit train images. So this is the X train labels. This is the Y. And you train it for 10 epochs, and then you give you give something known as in the validation dataset, which the model does not use to train itself, but which you can track at the time of training. So you can pass this as a tuple to the argument validation underscore data. So now you will evaluate the models. On X axis we have the epochs, on Y axis we have the accuracy. So the orange line shows the validation accuracy, the blue line shows the accuracy of the training data. So your simple CNN achieved an accuracy of 70%, not bad for a few lines of code. For another CNN type, so you should check TensorFlow Kickstart for experts. Okay, we have already seen that. Okay, so we will continue in the next class. This is taking more time than I thought, but next class definitely we will be able to finish convolution neural networks. So if you guys have any doubts, any questions, anything to discuss, let me know.
Sir,
Yeah.
sir, how the activation function affects the algorithm?
How the activation function affects the algorithm?
Yes, sir.
Can you